Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. So welcome. This is a supplemental lesson. I'm calling this part 10.2 because I realized that although I did a pretty comprehensive treatment, at least at the introductory level of Bronsted-Lowry acid-base theory, right? We did identify the Lewis acid-base definition as something that was also relevant to organic chemistry, and it certainly is. It may not be quite as prominent as Bronsted-Lowry. I don't know. It depends. It depends what type of organic chemistry you're talking about, but it is found commonly. So let's at least say a few things about Lewis acids and bases in organic chemistry. So if you recall, Lewis acid, Lewis base definition is the broadest, most general definition of what it means to be an acid or a base. Here are the definitions. An acid is any electron deficient species. A base is any electron rich species. Can we give some examples? Yes. So here are some examples of electron deficient Lewis acids, right? Pretty much any metal, cation, metal ion, right? Which are all cations, whether they're main group metals or transition metals, whether they're +1, +2, +3, +4. These are positively charged species, and by definition, they're electron deficient. Very commonly, boron and aluminum compounds, because remember, these are octet deficient elements. They only have 3 valence electrons. They can only make 3 covalent bonds. Therefore, there are 6 electron species, and by definition, electron deficient. Carbocations are also in this list. What about bases? Pretty much any element that has at least one lone pair: nitrogen, oxygen, phosphorus, sulfur, halogens, except for fluorine, 2 electronegative. Interestingly, the pi bonds in alkenes and alkynes, the pi bond system in benzenes, these can also be considered Lewis bases. Okay, let's take a look at some examples, some actual examples. Here's an example from benzene chemistry. In fact, this is electrophilic aromatic substitution. And in this reaction, one of the ring hydrogens is replaced by a halogen or some other electrophile. In this case, chlorine. You can see that when we attempt the reaction above, in the absence of a Lewis acid, it takes a long time and we get a poor conversion. However, when we add the Lewis acid, ferric chloride, iron 3 chloride, the reaction is greatly facilitated. You can see that. And so, of course, this is use of a Lewis acid as a catalyst. Here's another example, also from electrophilic aromatic substitution. This is Friedel-Crafts alkylation. The reaction between the tri-substituted benzene derivative on the left and tertiary butyl chloride on the right takes 24 hours to give a low conversion of the product, the T-butylated ring, whereas if we use the Lewis acid aluminum chloride, there's aluminum, right? Again, you can see, oops, my error, that 30% should be 80%. In the below reaction with the catalyst, that's now 80%, not 30%. Sorry about that. All right, and then here's boron. I would say between boron and aluminum, I'd probably say that boron is probably the most commonly seen or used element for Lewis acid mediated organic reactions. This is boron trifluoride etherate, right? The dimethyl ether above, the diethyl ether below. And so you can see that in the above reaction, we accomplish a ring closure. In the bottom reaction, we accomplish actually a ring opening of the strain 3-membered ring. Very different reactions, both promoted by the Lewis acid. Well, this is actually the last slide in this brief presentation. The idea here was just to acknowledge the existence and application of Lewis acids and bases in organic chemistry in a very introductory manner. And so let's at least say something mechanistic about this. I mean, how mechanistically does this work? Well, if we look at the formation of a Lewis acid-base complex and the formation of what's called a dative bond. Now, a dative bond is a covalent bond where both electrons in that covalent bond originate from the same atom. So here is a classic Lewis acid-base reaction between boron trifluoride and diethyl ether to form boron trifluoride diethyl etherate. And so you can see that boron, again, electron deficient, using all three of its valence electrons for the 3 bonds to fluorines with a total of 6 electrons for its octet count, very much wants to complete its octet. And so the reaction is actually involving one of the lone pairs of the oxygen in the ether as a Lewis base, forming a bond with the empty p orbital of the sp2 hybridized BF3 to form again this plus minus overall neutral dative bond complex, right? And so you can imagine that in the use of, say, boron trifluoride etherate, and you saw several synthesis examples of that, that ether ligand can pop on and off, right? This reaction is fully reversible, and the BF3 can complex, say, with another lone pair in a molecule or a pi bond and exert kind of a pull on that bond and promote a reaction. So again, this is just, I know, very cursory, but I did want to at least complete our definitions, our acid-base definitions. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.